Welcome to today's Research Pays Off, and I will hand it over to them.
Thank you, Lauren, very much, and thank you to everyone who's connected here for this NRRA Research Pays Off webinar today. Today's webinar is really reporting on a project that just ended, that essentially started, unfortunately, during COVID. So it did have its own struggles early on, especially first 2 years of the project were in the second half of 2020 and then obviously 2021. This project really focused on looking at what type of lab-based measures we can use in order to screen some of the sources of materials, specifically things like binder sources or recycling agents, especially when it comes in context of using recycled asphalt pavements or reclaimed asphalt pavements. So it was a joint effort that was originally proposed to NRRA as part of one of the calls for innovations. And the idea was to come up with a method that can allow us to look at compatibility between different type of systems. So it was a joint effort between us at University of New Hampshire and Cargill Industrial, who are partners on this project. I So if you want to go to next slide, Shivam. Yeah. So the overall motivation, as I said, is really to look at as our asphalt mixes are getting more and more complex with presence of recycled asphalt materials as well as things like recycling agents, and especially also as our binder sources are becoming more and more variable, since binder trading is really tied to crude oil trading, and depending on the daily price indexes, there's quite a bit of variability in which source of binder you end up using for that day's production. The idea here was to try to provide a mechanism that's more at a binder source or material source evaluation basis, not necessarily something that replaces things like balance mix design or day-to-day production controls, but more a tool that can be used prior to manufacturers or agencies considering different streams of products. And keep in mind that while there is obviously a chemical incompatibility or physiochemical incompatibilities between these, in context of this project, we tried to keep it more practical. So compatibility here is defined more in context of what you expect as a performance, because that's really where the rubber meets the road at the end of the day in context of pavements, and that was the focus here. So what I'm going to do is actually hand it over to Shubham, who is the PhD student who worked on the second half of this project, and have him go through the key things that we learned here. The final report is in 508 compliance review right now, I believe. So it will be published soon and available through NRRA. We cannot capture everything that went into this project. As I said, this project really spanned over about 4.5 years, and a lot of work went into it. But you'll get to see the cross section of that information.
Thank you very much, Dr. Dave, for your introduction. And I'll go over the study objective, what our research was guided to achieve. So we had like three key objectives, and the first one is to explore the practical and implementable compatibility characterization system in the context of combination of various asphalt sources such as virgin binders or the binders from the reclaimed asphalt pavements, and the second one was to evaluate the compatibility between these asphalt binders with the recycling agents. And the key second objective was to build a methodology for adopting this characterization system. and finally to provide guidance to agencies on implementing these methods. With this, our research approach started with the literature review and material selection. We had covered the literature outside of the asphalt domain as well. And we came up with the uh, core material sets and the 8 validation mixtures. And in core materials, we have selected binders which had the known compatibilities or incompatibilities historically. And then we had explored the analytical methods such as differential scanning calorimetry, thermogravimetric analysis, SARA fractionation, and elemental analysis. And then we covered the binder performance testing such as linear viscoelastic analysis, linear amplitude sweep, and multiple stress, creep, and recovery tests. And we concluded with the mixture performance assessment such as from cracking perspective, cracking performance tests. And this slide is showing the simplified or the flowchart version of our research approach, which we started with the selection of core materials, which included 3 binder sources, 3 wrap sources, and 2 RAs, followed by the mix design and production of mixture combinations such as like virgin, low wrap mixture, high wrap mixture, and high wrap treated with RAs. In low rep mixture is the difference between these low rep and high rep mixture is just the percentage of the rep incorporated into them. Low rep mixtures includes 25% of rep content in it, whereas high rep mixtures contains 45% rep in it. Then followed by the binder extraction and recovery and PAV aging on those blends. And then we had proceed with the laboratory characterization covering the binder tests as well as mixture tests. On binder side, we have evaluated the rheological characterization using DSR and thermal characterization using DSC. And these methods are covered into this presentation, and the remaining methods are in the report as said earlier. And in the mixture side, we are covering here complex modulus test, Illinois flexibility index test, and DCT test. Then followed by the statistical analysis for finding correlation on mixture side and binder sides, and followed by the validation of the findings from the core materials, and then ending up with the recommendations for binder and mixture performance parameters. So this table here shows our core material matrix, which includes 3 wrap sources, 3 binder sources, and 2 recycling agents. And these materials were meticulously procured in a way that two wraps are sharing the similar extracted binder performance grades, so that we can compare or make our conclusions based on the performance compatibility perspective, rather than PG is playing role in the research as well. And the same goes with the binder selection as well. 2 binders were sharing the similar performance grade. And recycling agents, one recycling agent was bio-based and the other one was selected from petroleum-based recycling agent. And with these combinations, we have generated 27 binder blends, which included 3 virgin binders, 3 low rep and 7 high rep blends, and 14 RA-treated high rep blends.
Yeah, just to make one comment on the blend side, just to be consistent, the blends were not primarily made as just blending the binders in lab, rather to be consistent with the mixed test results, because we wanted to compare between the binder properties and mixture properties. Actually, the test results where you see blend results are materials that were recovered from asphalt mixture. So for example, for a high rep blend, we'd actually have a lab mixture with high rep amount, where we would do the mix testing, and then also some of that mixture would be put through extraction and recovery, and that's what would give you the binder, just to eliminate another variable of some differences that you may get when it's not gone through the mixture production.
And as discussed, we evaluated these two test methods in this presentation. And on the mixture evaluation side, we generated the 21 mixtures and 3 virgin mixtures, 3 low rep mixtures, and 9 high rep mixtures, including 6 RA treated mixtures as well. And the one thing that we have taken care here is that we ensure the similar gradation and comparable volumetrics for all these mixtures to avoid the variations from those sides.
And the same aggregate source.
And yes, the aggregate source was also the same in this all mixtures. And mixture tests are shown in the picture form here as well. And we can now go through the binder testing results that covers rheological and thermal analysis. We started with the PG evaluation of the binder blends. And before we go into results, I want to go through the color scheme of these charts and patterns into it. So the black color here shows the high rep 1, which was our control rep as well. And the gray one is showing the low rep. Here the rep source is same. And the blue one is showing the rep 2 source, whereas the purple one is showing the rep 3 source. And the solids are without any recycling agents into them, and patterns are having recycling agents into them, whereas coarser pattern is showing the use of RA1 into them, whereas the RA2 blends are shown with the finer patterns. So here, as we can see in the STPG, the inclusion of RA resulted into very small variation compared to the low temperature side changes. And RAP1 blend have the warmest LTPG with all binders among all RAP materials. And here with the aging, we have observed that binder B has higher aging susceptibility than the binder C, even though they had similar performance grades. And to discuss the delta TC parameter, here what we observed is that the aging susceptibility of binder B was also observed here. And here we can see that inclusion of recycling agents sometimes negatively impacted delta TC, meaning that it moved to more negative side. So we went further and evaluated the component parameter TCM as well. And here we can see that the inclusion of recycling agent improves the TCM parameter, but however, as it is a composite parameter, the relative changes of TCM and TCS results into the delta TC that is showing the negative impact. And therefore, delta TC should be evaluated in conjunction with TCM as well. Then discussing about the black space results, here we can see that in general, addition of the rep resulted move the points towards the left top corner, whereas the RA addition reversed this process and moved to the bottom right corner. And here, as we can see here, that the in this plot, triangles are representing binder B results and circles are representing binder C results. And we can see that in virgin state, both had comparable values to start with, whereas inclusion of RAP, binder B and binder C, the RAP inclusion resulted into higher differences between those two blends, and which was true for inclusion of recycling agents as well. And binder B blends were crossed the warning limit of 180 kPa. And on the impact of aging side, the binder B blends with all the aging levels, it ended with inferior properties among all three binders. with this, I'd like to go through the DSC discussion, and Hassan is on maybe on the call. Yes, and he can add on this if I miss anything. Yeah. So here is the typical the heat flow diagram generated from the DSC testing, and this is the first derivative of it, and here we can see that this first derivative curve is assumed as a as a combination of two curves, having the primary curve and secondary curve. The primary curve is more related to the uh, Virgin binder, which is giving the glass transition temperature more negative side, whereas the secondary peak is contribution from the wrap binder. And the higher the phase separation between these two materials, the broader this graph will be. And so for higher or better compatibility, we want this distance as minimum as possible. And so the parameter side of this is that we can see that the glass transition temperature corresponding to this primary peak is called Tg alpha, and corresponding to secondary peak is called Tg beta. And the area under the primary curve is called the phi alpha parameter here, and the corresponding for secondary curve is called phi beta parameter, and that is normalized with the total area covered under the curve.
Thank you, Shabam. Maybe I can also add a little bit, a couple of additional contextual comments. I think if folks look at the blue line in the left hand, that is the normal glass transition type of curve most folks would see when they run a DSC testing. And just looking at that, it does seem like you have a single broad transition, which is what most often is being attributed to the asphalt binder. The reason we really go to that first derivative is what Shubham said, is because it allows us to actually analyze what is happening at the glass transition region at a much more detailed level. And this is important. It's coming from the polymer industry, where polymer compatibilities are assessed by whether or not we have a combined glass transition or a single transition. The more miscible those polymers are, the more of a single event you see. And we're using that same method here to really scrutinize the glass transition behavior of bitumen and see what the quality of that curve is. Do we have a single clean glass transition, or do we see a secondary transition occurring? And with aging and wrap, does that become further degrade or devolve? So that is kind of the background here for why this is being used as part of this compatibility analysis, and why the ratios and the relative ratios of alpha to beta are of importance to us.
Yeah.
And here, as discussed, the TG alpha parameter and TG beta parameter are shown in graphical format, and we can see that the inclusion of RAs clearly indicated the improvement in TG alpha and TG beta. And especially if we look on TG beta side, the inclusion of RAP negatively impacted, moving it to the more positive values. And the RAs reversed this trend and moved it to more negative direction, that is desired one. And RA1 is clearly showing better improvement than RA2, meaning that RA1 is potentially better compatible with than RA2. And coming to the mixture result side, we started with the complex modulus testing, and on the right hand side it shows the Glover row parameter on the mixture side in the black space, and addition of RAP is moving the points towards the left top corner, whereas the rejuvenation improved it and moved it back to the right bottom corner. And here we can see that mixtures with both RA1 and RA showed the lower E star and higher delta value, showing the improvement, whereas RA1 is generally resulting in larger reduction, again indicating supporting the results from the binder side that we observed and showing higher effectiveness. And mixtures with binder B shows the lowest compatibility with control rep and RS.
See if Hassan has any additional comments.
Yes, Hassan, if you want to add anything or. Okay. Then coming to the intermediate temperature properties side, we conducted the I-fit testing, and here the white bars are showing the virgin mixture results without any recycling agent or wrap into it. And here we can see that inclusion of the wrap clearly negatively impacted the results. And on binder B and binder C side, as they are having similar performance grade, we can see that binder B had very negative impact compared to binder C on the low wrap mix side. And again, showing the incompatibility of binder B than binder C. And RS improves the fracture performance properties at intermediate temperature, and again RA1 is showing better improvement. And uh, the low temperature side, we conducted the DCT testing, and this is the fracture energy obtained from that. And we can clearly see that virgin mixtures had better fracture properties than the mixtures having wrap into it. However, the inclusion of RAs resulted into more negative impact on the fracture energy. But here, as we can see in the second graph, that FS that shows the FST parameter that is normalized, fracture energy normalized with the peak strength, and we can see that statistically the RA had no impact on the results, and uh, that RA1 is showing better improvement in with the case with binder C. And however, this trends in low temperature side is not that consistent as we observed in the intermediate temperature properties. Now discussing about the statistical analysis and correlations between these mixture properties and binder properties. So binder properties are shown in rows and mixture properties are shown in columns. Here we can observe that the mixture properties at intermediate temperatures such as Fi, RDCI, and Clover row parameter had overall better correlations with the binder parameters, rheological especially, and on the low temperature side, mixture parameters such as FST has shown comparatively good correlation with the DSC parameter than the rheological parameters. And TGAV parameter has shown the good correlation with all the mixture properties. And these are some of the example plots of the good correlation that are shown previously. Now coming to the validation materials testing side, and this table is summarizing all the validation materials considered into this study, and the percentage rep and percentage res here represents the RBR or recycled binder ratio in the mix, and the virgin binder grade is also shown in this column. Then coming to the binder testing side, we have looked into the black space and delta TC analysis that were identified from the core binder testing. And here we can see that both the NCAT mixtures are crossing the limit of cracking limit of 600 kilopascal, and all validation materials have better delta TC values after one-time PAV aging, and we can observe that the NCAT 30 and NCAT 45 mixtures. So NCAT 35 mixture only had 30% wrap, whereas NCAT 45 mixture had 45% wrap into it with recycling agents. So here the recycling agent is working well, and it is neutralizing the effect of additional wrap we are considering into the mix. And it was true in TCM property as well. And again, showing the effectiveness of recycling agent into that mix. With this, here we are discussing the thermal analysis from BSc testing. And we can see that TG alpha is more resembling to the trend of LTPG of virgin binder or virgin binder, including the RAs. And on phi alpha side, here it shows more discriminating trend in a way that the Missouri mixture here had the highest RAS content, and it clearly shown the effect of a higher RAS content into it by showing the lower values of phi alpha, meaning that the higher phase separation, and it differentiates between the binder sources. And if we had the same binder source but different wrap content, it was also able to capture that effect. And mixture result side, at intermediate temperature, we can see that only Missouri mix is passing the threshold of 8, whereas all mixtures having minus 22 pg was shown very less Fi values, as shown in this arrows. So the Missouri one was having the minus 34 binder into it, whereas this three mixtures had the minus 28 binder grade, whereas all these lower values had minus 22. And therefore, somehow we have to come up with the testing temperature selection that incorporates the binder PG into it.
Location PG at least.
Yes, and the location P from LTPP bind dataset as well. That leads to the low temperature testing, and here we have selected the temperature based on LTPP bind dataset, uh, depending on the geographical location of that location. And the fracture energy here is showing that uh, only NCAT mixture is passing, along with Virginia mixture, they are passing the threshold. However, in FSD parameter, that it discriminate more compared to the fracture energy, and these are this was in line with the findings from the core mixture as well. And here showing the statistical analysis example of correlations, as shown for the core mixture, core materials, that again delta TC and TCM were showing good correlation with the mixture properties, and FST parameter is showing good correlation with the DSC parameters. And coming to the summary of from the binder perspective, is that rheological properties such as Clover Row, TCM, and TG, they are able to differentiate or characterize the wrap sources, and along with the binder sources and differentiation as well. However, the deconvoluted DSC measurements, they were better in distinguishing the RA effect with a higher confidence than the rheological parameters. And as discussed, the delta TC should be evaluated in conjunction with TCM, as most of the binders nowadays are M controlled binder. And TGAV parameter, as it has shown good correlation with mixture fracture parameters, it can potentially be used for the preliminary material screening. And on the mixture side, the complex modulus test like confirms the findings from the binder testing, and it differentiates between the binder sources. And for intermediate temperatures, FI and RDCI from IFIT test, and Glover row parameter demonstrated the high potential ability to distinguish between these mixtures. And for low temperatures, FST is appeared to be more discriminating than the fracture energy by itself, and binder grade effect should be accounted in the intermediate temperature characterization. And finally, the recommendation of this study was that rheological evaluation should be conducted to characterize the virgin binder and wrap sources, and especially Glover row, delta TC and TCM parameters. And for higher or better confidence for the RA evaluation, the DSE testing is recommended along with, and for that TG, glass transition and related parameters. And for mixture side, IFIT and DCT tests, and FI and RDCI from IFIT test, and FST parameter from DCT test are recommended. With this, I would like to thank you for your attention, and I'll be happy to answer the questions that you.
Just if we could go back to the recommendation side, I'd just like to add two or three more things on this, and these are in the report as well. Please keep in mind that majority of the testing effort on this project was wrapped up probably almost 2 years ago at this point in time. Obviously, we keep on working on these topics. So, for example, you see on the DCT test, we proposed, or what we learned from this effort was that the fracture strain tolerance, and if you're not familiar with this parameter, all it is doing is trying to capture some of that post peak shear. Just to also mention on top of that is we have an ongoing effort that's doing a more detailed evaluation of that post peak shape. So it's likely that as we learn more things with other indexes such as post peak index, which is being developed in that ongoing study with MnDOT and Minnesota NRRA, it's likely that in future we should revisit this data set and look at those parameters as well. When we did this study, we used what was readily available to us, and at that time the two parameters that were readily available for that particular test, for example, were fracture energy and fracture strain tolerance. Same thing is true on the complex modulus side of things, on the rheological side, on the mix as well. We used the Glover row mix parameter also in the mix characterization because that was available. I know people are also looking at more shape parameters there. So I think in future there'll be opportunity. But the message I'm trying to convey here is that obviously these studies are done at a given time, and as we learn more, the data sets are always available. And since these are through efforts like NRRA, all of that data set is available to anyone to apply those additional parameters, and that should be looked at in context of recommendations. We should not just close the book on the study and say that's it. The bottom line was this effort allowed us to gather all this data. It's all processed, it's all tested, and we made recommendations based on what was available to us at that point in time. But as we learn more about these mixtures and their cracking processes and so on, we can continue to revisit and look at those sets of data. The second thing I wanted to mention, and we did not explicitly put a slide here, but tremendous thanks to many NRRA member agencies as well as other NRRA folks for helping with all of these material collection effort. There was a big challenge, especially because when we are gathering material, we were in COVID shutdown period. So lots of thanks to the agencies, Illinois DOT, Missouri DOT, Minnesota, obviously, Wisconsin, and others that really helped us gather these binders, wrap sources, mixtures that made it possible for us to do this evaluation. So with that, I'm sure that people have questions. So yeah, feel free to ask them. I see Lauren, you turned your camera on, so I'm also trying to keep an eye on the questions or chat window.
Yeah. Oh, we just have a comment and question in the chat
Yeah,
from
Amy, yeah. Yes.
from
So
Amy.
Amy, good question on
Oh.
what, yeah. Go ahead.
Did you want me to read the question?
Sure.
Okay. So Amy says, thank you for the comprehensive presentation of extensive work. Can you please redefine RDCI?
Yes, and thank you for that question, Amy. And as Shubham was going through this presentation, I was also thinking same thing. You know, sometimes we get used to certain terminology, but we should probably provide some background information on what these indices are. RDCI is a parameter that we had proposed and developed in 2019. It's essentially once again trying to capture the shape of load versus displacement curve from any type of fracture test. What it uses is a cumulative work. So if I don't know, Shubham, if you have a slide that shows general fracture test results.
Can just
Okay.
comments.
Yeah. So it essentially is taking the general shape of your load displacement curve, but instead of just looking at load and displacement, if you take the accumulation of that work as the test progresses, it's essentially using the rate at which your fracture work is occurring. In other words, it's trying to capture the rate at which material is dissipating the energy within your fracture test. And it's that parameter. I can share there's a paper that we did in 2019 on it and be happy to send it to you just to make sure that's included. And also in the report, it's obviously described as well.
Okay, thanks.
Yep.
And then Michael just made the comment, thank you to the research team for working through this project during COVID uncertainties, shutdowns, etc. And we just got another one.
Yeah, thank you, Michael, because Michael's also been the technical liaison on this effort and provided support throughout the project.
Yeah. We got another question from Daniel. Any potential reasons why certain wrap sources might be showing lower compatibility? Is it wrap aggregate type binder or something else?
Based off of both mixture and binder testing, Dan, our take on it is it's predominantly binder as to the binder source that was originally used in that wrap, and also what type of aging it had encountered over the course of its original service in the pavement. So that's at least what is my take based off of all the data that we looked at in this project. I don't know, Hassan, if you have anything additional to add to that.
Yeah, no, that would have been how I would have responded as well. I think we see a good correspondence between our binder and mixture results on those incompatibility assessments. So it does seem to be very much dependent on how that, the bitumen source and the degree of aging, oxidation, and degradation that's already occurred on it.
Two questions here. One is, well, the title of the presentation is Practical Approach and Implementable Research, but you guys are showing like 3 types of tests. So my question is, from the practical perspective, should I just do the binder testing, or the rheological typical binder testing, or the glass transition assessment, or the mixture? I should just go and jump into the mixture testing, but you guys are showing like overwhelming amount of testing there in the recommendation.
Yeah.
So to be practical and to print specs, what is the most likely one that I should just use? That's the first question. The second one is for Hassan. Do you guys consider the mastic for the glass transition assessment and for this assessment? If you recall all the work that we did in Wisconsin, once you add the fine aggregate into your you combine it with the binder, the glass transition, all that mechanism changes. The compatibility. So that may have an impact on your overall performance and explanation of why you have these correlations. Did you consider it mastic at the beginning and you decided not to do the assessment? Do you have any rationale on that? Thanks.
Hassan, do you want to answer the second question first, and then I can tackle the first one?
Yeah. So I'll answer the DSD part of this. So using the TG portion of this. So using a DSC, we've got about our sample size is about 5 to 10 milligrams. So it is not very feasible to add a mastic impact or fillers into a samples at a representative level the way as you point out, dilatometric methods with a much larger sample size would allow. So the mastic interaction factor is not being considered in this. Not to say that that doesn't exist, but that within the tools that we would use and the way to be able to have the type of bitumen multiple peak analysis that you would be able to get with a DSC, it really would not be possible to include a mastic impact in there, which is, and I'll, I don't want to answer on for Eshan. I'll just give you my impact. I think that the TG tool here and the DSC was very much meant as a method to validate other methods and a way to provide some context and grounding for what we're seeing in the other methods, and not necessarily as the leading method for folks to use in a specification. I think that some of the other methods, especially the mixed methods, to show that we're also detecting some of what we're seeing in the binder, would be able to take a lot more of those factors into account. So I'll leave it at that and hand it back to Eshan.
Yeah, thank you, Rahul, for those questions, and they are very good questions. I will first say this, that in actually the first round of testing, we did use very heavy-duty analytical methods to evaluate these materials, especially the binders, using a lot of let's say chemical and physiochemical testing, and the practicality here is relative. We are talking about still using laboratory mixed performance test, not necessarily. So essentially, it's not at the level where you would say that you're using this for something like a process control or a QA process type of practicality. We are going here more from something like 3 to 4 months of testing needed to just make sure that you are okay with a certain crude source. In general, to looking at more like trying to still do 2 weeks of testing or 3 weeks of testing type of practicality gain, and that's why it's really an innovation project, not necessarily a project where you have something that's ready to go into specification. It's more to provide tools to probably more to material suppliers than agencies as they are evaluating different sources of product streams. But as Hassan said, our recommendation is more geared towards the mixture testing side of things, with binder testing providing a little bit more understanding of what's happening behind the scenes.
Thank you so much. Outstanding work. Thank you.
Thanks, Rahul.
Any other questions or comments? All right. Well, hearing nothing and seeing nothing in the chat, we will conclude for today, and you can look for the final report to be published soon. I would hope in the next month or so we're going to get the ADA compliance completed, and then we'll be sharing that when that's available and ready to review. And you can watch for that on LinkedIn and maybe in email as well. So thank you all for joining us. I'm not sure if we will have a session next month, but you can watch for an announcement. And we hope you have a good rest of your day. Thank you.
Thanks, Lauren. Thank you all. Bye-bye. Yeah.
Thanks, everyone.